We have talked about graphs. We have talked about the directed graphs, undirected graphs. Also, we have talked about weighted graphs. Now let's do some let's talk more about the features of a graph. So in an undirected graph, as you see, the graph is symmetric. So a symmetric graph is a graph that if there's an edge from A to B, so there are also an edge from B to A. So, and also we have another feature that in undirected graph or in symmetric graphs, if you have a matrix A, that's the matrix A is the adjacency matrix of graph G, then it's also equal to the transpose of the matrix A. So in the symmetric graphs, that also all undirected matrices are symmetric. So the adjacency matrix is equal to the transpose of the adjacency matrix that is A, and we are showing with the T above the A. So also we have another kind of graphs that are reflexive graphs, that are if there are a link from every node or every vertices to itself. So from every vertex to itself, if there's a node, if there's an edge, so we call this graph a reflexive one. And it means that on the main diagonal of the matrix, all the values are 1 if there's unweighted. If they're weighted, so it's just going to be some other values other than 1. Okay, so that's going to be a reflexive graph. And definitely the antisymmetric graph is a graph that is not symmetric. That means that, for example, if there is an edge from a node A to B, it might not be as like an edge from B to A. So that's called antisymmetric. And for sure, on antisymmetric graphs, A is not equal to transpose of the matrix A. So that's going to be some features of the like the graphs. Okay, and now we're going to talk about the traversing a tree. So that's going to be our next topic. That's going to be talking about how we can traverse through a graph. So now we're going to talk about traversing a graph. Traversing a graph is very similar to traversing a tree. As you remember, when we talk about traversing a tree, we had two ways. One was the depth first, and the other one was the breadth first. So, but there's something that you should remember when you are traversing a graph, because the graph may contain cycles. So it might be possible that we get trapped in cycles. So to avoid that, we may use another data structure to store the status of visiting nodes in a graph. So for example, let's say that we have a graph G, and in the graph G we can, like for example, create a vector or an array, the array of or vector of the booleans that says that if we have visited a node or not. So here is the depth first algorithm for a graph. So first of all, we are starting with some node. Let's say that we have a node, like let's say A, B, whatever we have. Then we are visiting that node. So the important thing is that when we are visiting that node, we are marking that node, let's say here is node V, as visited. So the next time that if we see this node, we are not gonna go through that node because we already visited that node. And then for every adjacent vertex U of this V, so let's say that the node V is connected to several nodes and U is one of those nodes. Okay, so for every adjacent vertex U, we are checking that if U is unvisited. So that's very close to what we have done here. So we are, if it's not visited before, okay, then we are checking that. Then we are calling the DFS again. So as you know that the DFS in trees was recursive, so also in the graphs it's a recursive function. So now we are going to go and do some tests and traversing a graph using a depth first algorithm. So here we have a graph G containing 4 nodes or 4 vertices A, B, C, and D. And here I have an array called V that says that if we are visited nodes, any nodes or not. So for at first all the values are 0, it means that we haven't visited any nodes so far. So let's start with node A. Okay, so we are passing the node A to the DFS function. So I'm gonna write DFS A, so I'm passing A to this function. Okay, then we are, based on the DFS, we are gonna visit A. So what happens that we are visiting A, so A will be printed, for example. Okay, and then what I'm gonna do is I'm gonna mark A as visited. So I'm gonna just replace this one and make the value of visited for A equal to 1. Okay, so now it says that for every adjacent vertex of node A, and as you see, node A is only connected to node D. Okay, so what happens is the next call will be DFS. Sorry, let's change the color. So the DFS of D. Okay, and I can call the DFS of D because D has not been visited yet. Okay, so this if condition holds, so it means that the D is not visited, so I can call the DFS of D. On the DFS of D, okay, so I'm visiting D, so I'm visiting D. Then the next step is to mark D as visited. So what I'm gonna do, going to this array that I have, and I am putting 1 as a value for D. It says that D is visited. Now next thing is for every adjacent vertex U, that in this case is A, B, and C, okay, I'm gonna call the DFS of U. So if, like, for example, we sort the adjacent vertices by name, so first we're gonna check the DFS if we can go and call the DFS for A or not, because A is the adjacent vertex of D, but we already visited A, so there's no no need to visit A anymore. So the next node we're gonna be B, and because D is not visited yet, so we're gonna call the DFS of B. So we're gonna call the DFS B. So DFS B, okay, so B is not visited, so we are visiting B. Okay, so we are visiting B, and then we are marking B as visited. So here I'm gonna go here and put 1 as the new value for the visited value of B. Okay, so and now for every adjacent vertex of B, that is D and C. So if we're gonna like to sort them based on name, so we'll have C. So I'm gonna call the DFS of, let's change the color. So it's gonna be DFS of C, and because C is not visited, it's fine. So I'm visiting C. Okay, now I'm going to this array that I have, this visited array, and I'm marking C as visited, so it's gonna be 1. Now for every adjacent vertex of C, that is B and D, but both are checked, both are visited, so I'm going back to where I call the DF like the B, so DFS of D. But in D, I've visited C, and also I visited B, so now there's no more call, so I'm going back, okay, to where I call the DFS of A. And because I also have visited every neighbor or every adjacent vertex of A, so now the graph, the traversing of the graph is completed. And as you see, first I visited A, then I visited D, then I visited B, and at the end I visited C. Okay, and this is the order. So here I started with A. Okay, so that was the first thing. I started with A. Then the next thing was D. Okay, because that was the only adjacent neighbor of A. Then between B and C, B was we sorted by name, so B was third, and the last one was C. That was the last node. So that's the first traversing of the three. Next, we are gonna like do the same example, this time using the breadth first algorithm. Okay. The next way to traverse a graph was the breadth first algorithm. Okay, so that's, as you see, is the first part of the breadth search algorithm. Okay, so we are at first making all nodes unvisited. Okay, so let's say we have an array, the size of the vertices, the number of vertices that we have. So first we check all of them unvisited. Then we are creating an empty queue. Okay, an empty queue. Then we can sort, for example, the first node that we have, we see based on the sorting the names of the graph on name, based on name. So we can put the first node on the queue. So on the second page, as you see, is the rest of the breadth first function. Okay, so we are adding that node to the queue. Okay, and while the queue is not empty. Okay, so that's the breadth first, also similar to what we have seen in trees. Okay, so while the queue is not empty, okay, we are dequeuing the node that we have, okay, in the front of the queue. Okay, so if the queue is not visited, so we're visiting that node, then we are marking the node that we are already visited, okay, to visit it. So because to avoid the getting trapped in a circle, okay, visiting a node many times, okay, so everything as visited. Then for every adjacent node or vertex of the node that we are currently visiting, okay, we are adding to the end of the queue. Okay, so every node gonna be to the, as is similar to the trees that we are visiting. Okay, so we were in the trees, we are visiting the root, then we are visiting the first row, then the second row, and also the rest. Okay, so at every level we are adding the children of the node to the end. So similar to that in breadth first, okay, we are adding every adjacent vertex of the node that we're visiting to the end of the queue. Okay, now let's go back to our example, and we can see that how we can, using the breadth first, we can traverse this graph. So here is my graph, graph G with 4 nodes. Okay, the same graph that we did the test and using the traverse that using the first search. Now we are using the breadth first search. Okay, again we have that array. All values are set to 0. It means that none of the nodes are visited. So we are starting with node A. So we are adding to the queue. Okay, to the queue we have this A. Okay, so we have this A. That's now we have this in our queue. Okay. So then we are dequeuing A. So node A will be dequeued, and we are gonna visit A. So I'm visiting A. Okay, so putting 1 here, marking 1. Then for every vertex that we have that are adjacent of the node A, we are adding to the queue. So also we dequeued A, so we are dequeuing A. Now we are adding to the queue. Okay, let's change the color. So queue will be in queuing D. That is the only adjacent vertex of A. So now the queue is D. Going back to the while loop again, so because the queue is not empty, okay, we are dequeuing from the queue. Okay, so D will be okay, so let's I forgot to mention that A is visited here. So we are dequeuing D. Now we are visiting D. Okay, so we are also dequeuing D here. Okay, now we are adding every node, every adjacent node of D to the queue. So we'll have our queue will be now B and C. Okay, I use this like way to show the queue, okay, but you should remember that like the first thing in the item will be dequeued first, okay, so that's the order, okay. So first we have like the B, like here it's going to be the first item to dequeue, and C is going to be the second, okay. Also I need to go and check the visited for D, okay, to visit it, okay, so it's going to put 1 here. Now for B, okay, I'm gonna sorry, also we forgot to add also A here, okay, so let me go here and add also A, okay, I forgot this one, so A also will be here, okay. So checking B, okay, checking B, so dequeuing B, so my new queue will be C, okay, A, I'm going to visit B here, okay, I'm going to visit B here, and then marking B as visited, okay. Now I'm going to add every adjacent of B to queue that I have, so my queue will be every adjacent of B that is C and D, so I'm gonna I'm gonna add yeah, C and D, so I'm gonna add C and D here to the end of the queue. Now the next thing, the first one on the queue is C, okay, so I'm dequeuing C. I will have A, C, and D, okay, and I'm here, I'm visiting C, okay, so I'm visiting C, put 1 here, and now every adjacent of C that is B and D, so I'm adding B and D to the end of the queue, okay. So let's change the color, so I'm adding B, and also I'm adding D here, okay. So the rest, I'm gonna like just to explain, because queue in the queue, the next item will be A, okay. So first I'm gonna see that if the visit A is visited or not, okay. Because A is visited, okay, I'm not gonna add the like visit A again. Also, I'm not gonna add the agents of the A to the list. So A will be dequeued, C is also gonna be dequeued, D is gonna be dequeued, B and D again gonna be dequeued, and at the end I will have a queue that is empty. So I will have an empty queue. That means that the breadth first is done. Okay, so that's the traversing graph using a breadth first search. Okay, as you see that we are similar to the trees, we are adding in the queue every neighbors or every adjacent vertices of a node.